This is a follow-up video to a video I posted in March 2021 when our gas boiler had just been repaired after it had been broken. At that time, that video was looking into what we were going to do next. This is the follow-up video really, so 2 years of research, lots of new products have come onto the market, new technologies have arrived, new ways of doing things, lots of expertise in research and understanding of various heating methodologies and products. And that's really what I've been gleaning and gaining over the 2 years, as well as doing our own testing at home. So let me talk to you a bit more about that. Gas boiler installed on the property when it was new. It's a Ideal Classic gas boiler. It's 17 kilowatt rated, which is massive rating, very overrated for the size of property, I feel. But that seems to be the case with gas boilers. It's not a combi boiler or anything like that. It's a normal gas. It does our heating and our hot water. Got a hot water cylinder in the airing cupboard. If you want to go back to the previous video that I did about it, it talks about our system in there in a lot more detail. It's running on normal wet radiator system, 17 radiators, and piped by 10mm microbore. Very simple boiler. It has two controls, an on-off switch and a temperature setting. And from May 2021, we have run it at #1, regardless of the temperature outside. There's no weather compensation or anything fancy like that, unfortunately. It is just an on-off cycling boiler. So it's not very efficient, and I'll talk more about that in a minute. But we decided to run a test to see if we could leave it at #1, the lowest setting possible, and still retain warmth in the house with our central heating. We don't use the gas boiler for hot water heating. That was turned off at the same time. So it's just space heating. The hot water is dealt with by excess solar using the eddi, myenergi eddi, either, as I say, from excess solar or from low cost overnight electricity to heat our hot water, which works fine. That's actually cheaper than using gas. The room thermostat in the hall is set, what was set to 21 degrees. As you can see, though, it's set to 10 now because the heating's off. But yeah, we set it to 21, see how we got on. I said about the boiler being old. It's a standard non-condensing boiler, not very efficient, as it says there, 76.9%. I suspect after 20 years it's probably more like 70% efficient, so not great at all. So these were some of the tests I did. On 26th of November, it was 11 degrees outside, central heating had been on. I went around a couple of radiators with a thermal imaging gun or infrared heat gun even, to see what the temperatures was. So this is the flow and return from the boiler itself. So 35.2, this is with the boiler running, and 34.1 return. And then in end of January, when it was 0 degrees outside, you can see there's a frost on the roof there. I repeated the process, this time looking at radiators. So this radiator is a double radiator in the kitchen. So you can see there, temperature at the bottom, temperature at the other side. I never know which one's the inlet and which one's the outlet, so I suspect the first picture is the inlet and the second picture is the outlet. This is the top corner and the other top corner. And then the thermal imaging of that same radiator, you can see the cool bit at the bottom in blue, slightly warmer bit in the just above it in green, then it goes to yellow, and then the hot stuff at the top. So it does indicate that our radiator and our radiators, because you'll see that on all of them in a minute, could do with a proper flush, because the system hasn't been flushed for years. This is a single panel radiator in the office. So top right hand corner, bottom right hand corner, top left hand, bottom left hand. So that's the outflow there, I think. And again, you can see not as bad as the previous one. The temperature is a little bit more even across the panel. being single panel, I guess. This is in the utility room. It's a very small radiator. Again, a single panel. So this is the first one in the series as well. This is right next to the boiler, so it's going to be the hottest. So that went to prove that we could run our central heating system with microbore at a low temperature, about 40 degrees, water temperature, sort of flow and return, quite happily and without a problem. And the house was comfortable. But during my research over the time, we have looked at various things but kept these constraints stroke requirements in mind when we're looking at stuff. So one, that we've got the microbore pipework. We can't go underfloor heating. We've got solid concrete floors, but we've also got solid oak parquet flooring throughout downstairs. So that's not going to happen. We could do underfloor heating upstairs, but it's probably more beneficial for it to be downstairs. And as I said earlier, we wanted to ditch gas, wanted to get off fossil fuels. So we have the gas meter removed completely, so we're fully electric. The heating options I looked at, the main ones were air-to-air with mini splits. So that's a smaller unit indoors, blowing hot or cold, depending on the option you choose. Then outside you have a heat pump. I looked at air source heat pumps or air to water heat pumps. I didn't look at ground source heat pumps because we don't have the space to put one of those in, so I ignored that from our option. I also looked at electric boilers. I discounted these options as well. Almost I looked at them and researched them. I have discounted them. LPG, gas, obviously a derivative of fossil fuels, as is oil, so I discounted both of those. Wood burning stove, discounted mainly because of PM 2.5 particles in the air and not being good for you. Far infrared, I have invested in. I have a couple of panels. I have 2 in the garage and 2 in the photo studio, and they work really well. However, the limitation is their efficiency. They can only ever be 100% efficient. I didn't really want to do the whole house in infrared because of that limitation on efficiency. I'm looking for the long term here. I want to do this once and not have to revisit it in 5-10 years time. Portable oil electric heaters and electric fans really go the same along the lines with far infrared, although they're actually more expensive to run than far infrared. I would have far infrared over the other 2 if that was the route I was going. Far infrared has its place, but not as a whole heating solution for our particular needs. The ones I narrowed down, I looked at in more detail in terms of pros and cons. Air-to-air heat pumps, mini splits. As you can see there, a minimum of 300% efficiency. So 1 unit of electricity in, 3 units of heat out. They also benefit from being able to do heating and cooling cycles. Very low carbon footprint with them. They can also be mounted higher up on the wall to minimise wall space, low-level wall space, and you can remove radiators to regain some of that wall space. They're certainly cost-effective to install if you're comparing it to an air source heat pump installation. Very low maintenance, minimal noise, and certainly safer than gas or hydrogen, which seems to be the popular marketing choice now with the incumbent gas industry trying to justify their future going forwards. But this video isn't about that. The cons with air-to-air is we still need a solution for domestic hot water, which you could argue we already have because we have the eddi in place. I would suggest it's perhaps not ideal for large properties unless you've got multiple units installed, or it's a very open plan and you can circulate the air well enough to heat the whole of the building. You're probably going to need additional ducting depending on the placement of the indoor units. It's also a different type of heating, so blown air rather than convection, which may not be suitable for everyone. And the units indoors can only either all heat or all cool in unison. You can't have one heating and one cooling. Not that you probably would anyway. That's heat pumps. It's worth an aside that on the March 2021 video, I looked at some of the constraints around our wet radiator system, and my concerns were the flow rates with microbore, performance in low temperatures, outside temperatures that is, electricity consumption, would we need supplementary heating? And since that video, technology has moved on, and there's lots of heat pump manufacturers now produce high temperature heat pumps, which, as it says there, will run exactly the same as a gas boiler in terms of temperature, so you can just do a swap for swap if you wanted to. I didn't specifically want to do that because I wanted to gain efficiency long term. Having a heat pump that runs at 60 to 80 degrees wasn't really an option for us because I wanted to gain the benefit from the efficiency of the heat pump, which you wouldn't get so much if you were running at such a high temperature. So these are pros and cons for the air to water heat pump or air source heat pump. 300% efficiency minimum, low carbon footprint. It can also provide domestic hot water. We can use our existing wet radiator system, can be tinkered with to improve efficiency in terms of flow rates and compensation curve and other bits and pieces to improve your efficiency. Low maintenance, minimal noise, safer than gas, hydrogen, and a more traditional heat source. The downsides are it certainly requires proper design and installation. You may need to change radiators depending on the type of radiator that you currently have. Come back to that in a bit. No cooling facility, certainly more expensive to install. Radiators can run at a lot lower temperatures, so it might take time to adapt. You know, if you touch a radiator and it's lukewarm, you might think the system's not working. Thankfully, we were used to that because of 18 months of running our boiler at number 1 at 40 degrees, so we know the feeling of the heat and the feeling of the temperature of the radiators. And yeah, it requires a bit more space for installation in terms of hot water cylinder and what have you. We then looked at electric boilers, certainly very easy to install and lower carbon footprint than gas. Also provide domestic hot water and use the existing radiator system. Very low maintenance, minimal noise, safer than gas, hydrogen, a more traditional heat source, and certainly more cost effective over a heat pump in terms of purchase and installation. The downside, as with a lot of electric sides of things like the near far infrared I was talking about, electric heaters and what have you, they can only ever be 100% efficient, whereas your heat pump can go up to 300, 400, even 500% efficiency depending on the installation, temperatures you're running at, etc. Which means that if they're only 100% efficiency, they could be expensive to run if you're unable to shift your energy usage and take advantage of off-peak electricity costs. So that's something to consider. With all of that sort of information collated, I felt I needed to understand what our house used in terms of heat, what it required to actually keep it warm. We know we could keep it warm at 21 degrees with the boiler set at 1, but what did that actually mean on paper? So I decided to start a heat loss survey, which meant getting out the blueprints from the original house, and then we had an extension which complicated things, and then I decided actually it's best just to start from scratch. So I got myself a laser measure and paper and went round and mapped out our whole house to create an online floor plan. So this is our 2 floors. Downstairs we've got 104 square meters, and upstairs we've got 65 square meters, so 170 thereabouts in total. Once I'd had that mapped out, I then also thought, well, let's get an EPC done, because we never had an EPC done, and I've got a friend who does them, so I collared him and he came round and did the EPC. What I've got up on screen at the moment is the existing ones with ours right at the bottom there, done on the 27th of March. And you can see there most of the people in the street are on a C or a D. We're on a B, so this is our outcome here. So current is right in the middle of the B. That's 86 with a potential of 90, so right at the top end of B. The EPC, as a lot of you may already know, is a bit flawed, to be honest. It hasn't really kept up with technology. I'll explain in a minute, because it gives us suggestions on what you could do to improve it. Here we've got a breakdown of our main components, which were very good to average to good, and some not applicables. This is the suggested improvements. A new condensing boiler, well, that was never going to happen because that would mean having gas, and you can see there's no option for a heat pump. So if you had a heat pump, it wouldn't make any difference, even though it's more efficient than putting a new condensing boiler. But here. And the other one was solar heating, and what Tom was saying was that unless the solar, like solar thermal with panels on the roof, unless it was a completely separate system, they don't count things like the eddi, where you use excess solar to heat hot water. It's not a separate system, it's sort of part of your solar, so they don't include it. But anyway, I was happy with B, to be honest. So you know, it's splitting hairs in terms of moaning about the EPC, but yeah, it is not fit for purpose, and I'm sure it will soon change. Other things I did, I researched and found Michael D. Poster's, hopefully I haven't butchered your name too much, Michael, some spreadsheets that he put together, very useful spreadsheet. I'll put a link down in the comments below. It was a coldest day spreadsheet where you could put in your usage of your gas, electricity or what have you, and then from there you could calculate what would be recommended for your heat loss, and that, as it turned out, was actually pretty accurate. Leading on to that, I commissioned a heat loss survey from a local heating engineer, JMR Heating. Mark came over and spent the best part of a day doing a heat loss survey, or probably half a day. He's part of the Heat Geek Elite team, and Heat Geek are very much in the forefront of energy efficiency, heat pump technology. By commissioning a heat loss survey from them, that I would get quality output. And they use a piece of software from Heat Engineer, and you can, if you wanted to, and I did, do your own. So I paid to do my own one before Mark came and did his. His was a lot more accurate than mine because I didn't really understand all of the terminology, but interestingly enough, the results are very, very similar. So this is designed, this heat loss survey was designed to look at us running at 40-degree flow temperature in our radiator systems with a heat pump. And you can see there that the total heat source required to heat the building when it's minus 2.4 outside degrees C is 8.4 kilowatts. This report goes very in depth. I'm not going to show you the whole thing. This is our worst performing room, which is the dining room at 25 square meters. It requires 1800 watts to keep it at that temperature. Standard radiators, blah, blah, blah. And it's not surprising really, because there's 6 meters of glass just on the patio. Then we've also got Velux windows above, 6 of those. And it's all open plan as well, so although there's some doors there that you can see, the rest of the room is open plan into the kitchen stroke sort of TV room. So you get a room by room heat loss in terms of watt hours per metre squared, with the worst rooms indicated in the colour there. So landing was the best room, can't camp out on the landing. And with the dining room being the worst room there. So this is the radiators. So I said earlier on we've got 17 radiators. So these are the types of radiator and their size and their output across all rooms. The majority of our radiators upstairs are this type of radiator in varying sizes. It's a single panel with fins at the back. There are all different types of radiators. They're either called K, start with K, or as I hear T. So we've got T1, T11, T20, T22 and so on. So 12 type 2s, type 11s if you want, and then 5 type 22s. So that's our existing radiators. If we wanted to run at 40 degrees, we would need bigger emitters, as they're called, bigger radiators. And this is the report here. There's about 5 or 6 pages of this. I've just shown you one. So take bedroom 1 for instance, top line there, room temperature at 21 degrees, current radiator is at the top in that pale colour, so it's K1, and it requires a K2 radiator in there. Slightly larger in height, but same width. And you can see the heat output there on that radiator would be almost 3 times the amount in terms of what was there before. But what it meant for us, if we wanted to go down the heat pump route, one radiator would remain as is, which was in the toilet downstairs, mainly because it was really difficult to get to and difficult to change, so that just decided it was easier just to keep it rather than try and change it. So we would need 3 Type 21s, 10 Type 22s and 3 Type 33s. And that's without changing any of the pipe work either. So we're still keeping the microbore pipe work. It would just be changing the radiators. The heat pump that was recommended was the Valent, 7 kilowatt. This is one of the new Aerotherm Plus heat pumps. They're made in the UK, actually they're in Belper, up in the Midlands. And there's a new factory there, that Valent factory that produces heat pumps. And this is a really efficient heat pump in a little bit more detail. So if you're looking at the 40-degree column there, 40-degree flow, you can get a seasonal coefficient of performance, so that's taken across the whole year, of 4 or 400%. So 1 unit of electricity in gives you 4 units of heat out. And as you can see there, the lower you have your flow temperature, the more performance you get. The higher the temperature, the lower the performance. But even at 55-degree flow, you still get 3 times the amount of heat out for 1 unit of electricity. Here is the noise side of things. The Aerotherm Plus 7 kilowatt, it's 55 decibels, which is just a bit above a whisper, very quiet. And depending on how far away you are from it will depend on how noisy it is. Now, because of where we were looking to locate a heat pump, we had to get planning permission if we wanted to go down that route. Normally, heat pumps are permitted development in terms of you can just pop it in wherever you want. However, there are a few constraints around that, and if you find that any part of the heat pump is a metre nearer than to your boundary, property boundary, then you have to get planning permission. So we did put in for planning permission because we were wanting to put the heat pump down by the side of the extension, and there's a sort of nice location there with the pipework that can then run up the side of the house behind the chimney breast, and you'll never really see it. The widest part of that is 1386 millimetres. With the heat pump in place, in location, with a gap at the back as per the recommended dimensions, it would be about 700 millimetres away from the boundary fence. So 12 inches. So for 300 mil, we've had to do planning permission. So that's going through at the moment. We should hear from that in the next week or two. Already talked to the neighbours to explain to them what we were doing. We've had the notice up on the lamp post. Yeah, I think we'll be okay there and everything will go all right. That's what we are going with, an air source heat pump, 7 kilowatt. And in the next video, I'll talk to you about costs, installation process, that kind of thing. But any questions so far, give us a shout down in the comments below, and I'll see you on the next instalment of our heating system. All right, take care.